number 9, number 9, number 9, number...
And that's the best part of this song, believe it or not. Anywho, let's get started. So here's our recap of a general weak acid being titrated by a strong base. We learned about all these different regions that we see throughout this titration here. And the way we would find all these pHs along the way is using the techniques we learned in the past. So pre-titration, calculate the pH as you would for just the weak acid by itself, because that's what it is. There's no base yet. Before you get to that equivalence region, you're generating a buffer. You can calculate the pH with the Henderson-Hasselbalch equation. The one point where you don't really have to do that, although you're welcome to, but we proved it, was the half equivalence point where the pH just equals the pKa. Very important in analytical chemistry for identifying your acid. We then have this sharp rise around the equivalence point, just like what we saw with the strong acid titration. But unlike that situation, the pH does not equal 7, but is greater than 7, because we've converted all of the acid into a weak conjugate base, and so we have to look at it from its point of view. And figuring out the pH in this case definitely involved the most legwork. After we go past the equivalence point, we enter this excess OH region, which was not new at all compared to the strong acid, strong base titration, because we're just assuming that from there on, we've used, in this example, 10 milliliters of sodium hydroxide or some strong base to neutralize all the acid. From then on, any strong base that we would add doesn't really have anything to react with, so most of it just stays in solution as hydroxide ions, which of course drives the pH high. And we can just assume that any hydroxide ions that are left over from that strong base are the main contribution of hydroxide ions. And we can just determine what that excess of hydroxide concentration is, find the pOH, and then find the pH. And so this brings us to a clicker. Now, we will do this clicker in Zoom, but check it out right now. Notice it's an identification question, one of our major questions in ACHEM. What do we have? We can figure it out from the data above. As for how we could learn how much do we have, like how do we quantify, we would need a bit more information. There's really two ways to do it though from a titration curve, and I'm going to cover both in homework 4. And I'm not going to cover it in lecture because I want you to gain some experience thinking for yourself through unknown situations. The good news is homework 4 comes with the solutions right away, so if you can't figure it out, you won't be penalized. You can always look at what I do and how I explain things, but definitely try to do it on your own because that's a really important skill in science and in this class. Take what you know how to do and figure out something that you don't know how to do. Now, what if you didn't have a pH probe to identify this sharp region right here? How would you find the equivalence point? Well, you would use something called an indicator. And if you've done a titration in some Gen Chem lab, you've probably used one of these before. In fact, you probably used this one over here called phenolphthalein. But notice there are many indicators out there. And we'll get into the logic of how these work later. But for now, just note that each of these indicators has 2 different color possibilities. And you'll notice there's this other column here called the transition range. Over these pH ranges, the indicator will change color from one to another. So for example, phenolphthalein will be colorless until it reaches a pH of about 8. And then, as the pH rises to 9.6, it will go from colorless to pink. And so you've almost certainly seen that color change if you've done a titration in lab. And we'll write some notes down about this momentarily, but really quick, let me just say that the choice of indicator is ultimately based on the transition range overlapping the sharp pH change that goes with the equivalence point. The reason why that's important is because imagine this titration's happening here. The pH is rising steadily, steadily, steadily. We get right behind the equivalence volume, and our pH is slightly below 8. And so something like phenolphthalein would still be colorless, but be right on the brink of changing to pink. And then you would add that tiny bit of volume, like a drop or two, and that would cause the pH to skyrocket because you're at the equivalence point. Now from just that tiny volume addition, your pH is above 10. which means according to this transition range, we would have passed through to the other side and the indicator would all be pink. On the other hand, other indicators with these lower transition ranges will have changed color over here in the titration. That doesn't mark the equivalence point, and it won't happen from one drop, because here it's not just like a little bit of volume corresponds to a giant change in pH. Only when the transition range overlaps the sharp region of the equivalence point does a small volume addition cause that color change to be complete. Now, I'll show you a visual later to try to make this more clear, but for now, let's just make some notes. The first thing we need to do is define something called the endpoint. Endpoint, not to be confused with equivalence point. It's a common misconception that these are the exact same thing, when in fact they are two completely different concepts that should both be reached at the same time in a titration, and I'll get more into that as we go. But for now, we will just define it. It is a physical change that should measure the equivalence point. Physical change that should, and let's put that in quotes and underline it to really emphasize that this word does not guarantee it's definitely going to happen. It just should happen. Physical change that should measure the equivalence point. But again, they are not the same thing, and we're really going to get into that when I get to the visuals on the next two slides. But let's keep writing some notes. Another term to define, indicator. Indicators are not magic, they're just an acid-base conjugate pair where the color changes based on which species is predominant. So acid-base conjugate pair. Acid-base conjugate pair that changes color based on which species is predominant. Based on which species is predominant. So for example, let's say we have an indicator in its acidic form, so it has a proton to donate. Instead of writing the usual A, let's write an I, and we'll just generically call this an indicator. But let's say it's like phenolphthalein, and that when it's in its acidic form, it's clear. But let's say that like any other acid, when it's in water, it dissociates to produce protons and leave behind the conjugate base. And this conjugate base has a different color, and it's pink. So when you first add an indicator to solution, if you're at a rather low pH, chances are the acidic form of the indicator will dominate and your solution will be this color. But then as you make it more basic, as you add more strong base, you start to promote the formation of the conjugate base, and meanwhile you lose some of this acidic form of the indicator. Eventually you'll have more of this pink conjugate base species than the clear acidic species, and so you see the color change in solution as it becomes more basic. And we want that color change to occur at the same time as the equivalence point. So let's just make a few more notes and then see some visuals. So first, let's say this. If the pH of the solution is less than the pKa of the indicator itself, then the acidic form, the HI form, will dominate. And what we would observe is a clear color, at least for this indicator. As we saw in the previous slide, other indicators have different colors. Similarly, if the situation is reversed and the pH is more basic, is higher than the pKa of that indicator, then the conjugate base form dominates. And in this case, we would see pink. Now, as for how I know which of these dominates based on whether or not the pH is lower or higher than the indicator's pKa, well, that I get from the Henderson-Hasselbalch equation, and that's something we'll cover more in depth in a future video. For now, it's enough to just know this. And so the way this works in practice is we use a small amount of indicator and we add it to the actual analyte acid that we're interested in titrating and studying. So only a few drops of indicator, enough to see the color change, but not enough to really impact the titration itself and affect our results. So let's write this. A small amount is added and is titrated along with the analyte. A small amount is added and is titrated along with the analyte. Along with the analyte. It transitions over a range around its pKa, not the analyte's. It transitions over a range around its, let's put that in all caps, its pKa, not, also in all caps, the analytes. The significance of that statement will hopefully become more clear in the following visual. But let's write one more line. Transition range should overlap the steep region of the titration curve to find the equivalence point. Transition range should overlap. Transition range should overlap the steep region of the titration curve of titration curve to find the equivalence point, EQ point. So let's try to make more sense of this with a visual.